Right, so this video is actually on a random walk, and I'm doing this in Python, and it's something that I constructed last night. It took an hour or so to do, and there's about 150 lines of code, so not too much. I made this file in the physics folder. I could have put it in a stats folder or somewhere else, but I made a file in the physics folder, and it's called random walk. So I'll close down this folder because it's not needed to give us a bit of extra space, and I will just zoom into the code. And what I've actually done, I could have done this in a Jupyter notebook, but I'm actually doing it in pure Python code. So when I zoom in, what I actually do is I break it down into little segments. So each part of it is a function on its own. So we've kind of like got our main function, and this is kind of like the standard pattern that I always have. So that's like our main function. And if I scroll down the code to the bottom, we call our main functions. We'll see that pattern. That's a typical pattern. And then all of our little components, and I built these up one by one, and I'll probably show generally the build up of what to do. But the first thing that I do is I have a template here, and this kind of like little area here is a template. And what happens is if we have this standard, this is called an idiom, like a standard pattern in Python. And if name equals main, then we run the main module, and everything can be called from the main module at this point in time. This particular main module is empty. But we like to refer to that kind of like right at the beginning of the code. At least if you do that, then you can kind of like put in other modules. So you can make other modules, well, not modules, but you can make other functions down below. So the main function is the main entry point for the code. I shouldn't call it modules, I should call it functions. So the main function is the main entry point for the code, and then we've got these other functions, and our main function can call our other functions like this. So that's just generally the pattern of how I build it. So we can have function 1 here, and we can have the first function, and then we can have function 2, and we can just call them sequentially. And by doing this, if we do this, and we can control the flow of the code just a little bit better, because we can kind of like pass the variables in that we want and pass them back out, and so like controlling the flow that way, which is quite nice. Functional programming effectively. So what do I actually do to start with, which is that, so we've got this if name equals main right at the bottom of our code. That's always going to sit there, and it's going to call a main module. But the first thing actually we want to do is well, understand what we're going to do. So we're going to do this random walk. What is a random walk? It is basically, imagine that we've got, or at least how I'm doing it is, imagine that we've got this chart, and then we start at a certain point. So I just say we start at the point 0, but we could start anywhere. We could start here, for example, but then we take one step, and we don't know exactly where we're going to go. We could go up, or we could go down, and we don't even know how much by necessarily. We're going to define those things. So we could go upwards to this point here, and we could go downwards to this point here. And when we've done that step, then we're going to, that's effectively our first step, which is, I mark it in green. That's our first step over here. So that's our first step points. Once we've taken our first step, we then take our second step, depending on where we are. Again, we might go up, or we might go down. And likewise over here, we might go up and we might go down. And so the pattern keeps on building. So that will be our, if I draw big fat circles there, this will be our second point, kind of like over here. Now these points may overlap and they may not. So, I'll draw them as not overlapping. So kind of like a binary tree in a way. That starts there and so forth. And we're progressing, and this is like our time axis here, and this is our potentially like our position axis, position over here. So that's effectively what happens, and we keep having these time steps that we go, and we're moving across in time over there, and our walk is taking a certain direction. Now we can only take one of these paths. So for example, we might have taken this path here, and that's effectively the random walk that we're going to try to plot. So we're going to do this like one random walk, but then we're going to do it 1,000 times. We're going to get 1,000 walks and kind of like see what happens, like see how this looks. Maybe we'll get one walk that goes down and ends in negative position. So that's effectively what we're going to do. This is used quite a lot for, it's used in physics, it's used a lot in finance. I used to use it a lot in finance, and that's effectively what we're going to be doing. So the first step of that is to just take one step. So I've made this function and I've called it random step. I haven't really commented it that well. I've just, you know, the doc string here is just let's make a random step. I could specify, you know, where we start effectively, which is when we drew the diagram. I showed it at the origin just for default, but you could start it, say, for example, 100 and move from there. But anyway, what happens, or how we define this, or how am I defining it at least? So I'm just saying that we've got this position here, and there's two components to this. One is what we call the drift, which is what I'm calling the drift, which is kind of like always, it's not almost like a wind blowing in a certain direction. So there's a propensity to always move in this constant direction, and this part of the random walk is not actually random. This is specified. Whatever the drift is, I've said it's 0.1. So it's kind of like for every step, go 0.1 up vertically. So that's one component here. And then if we took our next step, it would, so from here to here, it'd be the same. Now, if there was no volatility at all, this would be highly predictive. There's no randomness in it. So there we go. So it looks like that. These continuous triangles. So that's a straight line, no randomness. So, but nevertheless, it's our drift component that kind of like happens sometimes because it might be a wind, or in finance quite often it's the risk-free rate, which might be your drift component that goes in there. So we move on because we had that drift component there, but actually that's not the randomness. So we now want to introduce our randomness, and I just do something very simple to start with, but it actually turned out to be quite effective. So on top of our drift component, which was, I should actually redraw that. So on top of our drift component here, which was exactly where we are, we now impose this random component. I call it the diffusion. And this is effectively a random number. We'll go in and have a look at what this is. But our drift was this originally. And so this was our start point here. So we got start, which is this point over here. And then we got our drift term over here. So like how much to go up by. And then we have this extra term. So that's our drift term over here. And then we have this third term. This third term is the diffusion term. And that's this random number which goes from -100 to +100. It's a random integer between, and then we normalize it back down so it's between 0 and 1, just to have it kind of like at a same level so it doesn't move around, but we can calibrate it to what we like. So basically we've got this random number afterwards, and it's kind of like this error bar effectively. So we were going to land here, but now we can land anywhere inside of this error bar, something like that. And likewise, when we continue our walk, we might have started from any one of these points on the error bar. So we might have gone here, like here, for example. We might have arrived here, so we didn't arrive quite there. And then again, our walk. Now, our drift component, if it was continuous, would have led us to a point over here now. So we've got a modified drift, which is exactly this same step arrow over here. So even though I've drawn it badly, these arrows are the same size. And again, across this component, we've got this diffusion component, which is here, and we could arrive anywhere within this next diffusion. And again, this is kind of like what generates this random walk. So because we keep getting these continuous steps, these continuous drifts, but then we've got this additional volatility or diffusion factor, or whatever else you want, randomness that we've imposed on our system that we have no control over. So let's just see how that works. Now, one thing that we can do, because I've done it in a modularized way, is without showing the main part of all of this. So the main bit of the code builds everything. So we're not going to run the main code. I'm going to do like, in fact, I can comment it out from here. So we won't run the main code, but what we will run instead is our random step just to see what it actually looks like. And we don't have to put anything in here because we have already put a default value, so it's an integer of value 0 basically is what goes in here if we don't put anything. So we've got a default value that goes in here. We set our default value here by saying it's equal to 0. So that's fine, and we want to just show that this is like the result effectively. So the result is equal to this random step, and so what is this result? And so let's just print the result. And actually, one thing I might do is I guess maybe I'll put it down here, but or define this function, and then we'll call it _test. There we go. So it's kind of like we see it's grayed out here, and so instead of just running main, we can run this _test, and then we can kind of like switch it off when we want. So we'll go into this test function, and now the test function will do everything that we want. So we'll just label this is for testing. So all we're going to do is go into our main code. We're going to run a test function, and the test function is going to call this random step. This random step is going to start at 0, and then it's going to return something back, and we're going to be able to print out and see what we get back. So if we run this code now, and I hope that the flow of the code is relatively easy to see. We've got 0.49 that came back. Just draw the flow of the code. So we basically start here. We start at this point here at this if name equals main, and then we go and run this test function over here, and then this test function says, hey, let's go and run this random step function over here. That's basically the flow of the code, and it runs that little piece of code over here, and it gives us back this result, which is this little piece of code. It returns us this end thing which goes into the result, and we're printing that out. That's literally the flow of the code. So we go down to we read everything into our system, and then we begin to run it. Just remembering that Python runs everything from top to bottom sequentially. That's what it does. So we got 0.49, and we could try and run that again, and I guess we should get a whole bunch of different random numbers. There we go. We got a negative number this time, and we could even go run it a third time. We could say to ourselves, well, let's just run it loads of times. So for I in range, and then result like that. So that's now inside of a for loop, and we can sort of like run it 10 times, and we can print the result 10 times. So we'll get 10 sort of like different random numbers that go into our thing, and they're all completely different. Some positives, some negatives. Funnily enough, oh yeah, I was going to say that it looked like one positive, one negative each one, but just a bunch of positive and negative numbers. I might zoom in a tiny bit more, Control Plus, just so that everything's visible. So anyway, we now successfully have done our random step. So our random step works. We put this. We have a starting point, and if we don't set a starting point, then the start is 0, and then afterwards we get this number back. So we can. The next thing we want to do is effectively take our second step, and in order to take our second step, we had to retain some information, which was this result. So it's nearly like we want to feed this result back into our system, and one way of kind of doing this is say the result is equal to 0 to start with, and then here we can put in a result like this. Now, what's actually happening is when we go into our loop for the first time, we go in, and this time we're actually initializing it with a 0 value to start with. But then the result gets updated over here, and we get some kind of progression. So our step begins to look like a couple of steps. So if I press F5 to run that, we get a sequence of steps now all in a row, and they will incorporate to some degree our drift component as well, because that's part of our run. So we've got this starting point, which we set our starting point to be 0, but let's say we set our starting point to be 100 and run it like that. Again, we'll see like clearly what actually happens when we do this. Now everything's like based at 100 and sort of like randomly walking from a start point of 100. So we know that our function works, and we can take these steps just by feeding them back in. So whatever the step was, we're feeding it back into the system, and the only thing that we need to think about is the initial step over there. So that was our test, and basically, like, I take this concept over here and say, well, if we do one step, then we can sort of like create a random walk, and that's very similar. We've got this for loop pattern that comes in here, and what I will just call our feedback, which is that this result here keeps feeding back into itself, because every time we get this result, so it kind of like goes there, it goes back in, and then we get back this result a second time. So we've got this feedback loop that's going on effectively, and that's what creates our random walk. So I was doing this, and I actually started and I did it like this initially, because I thought that that's perfectly fine. When we're prototyping in Python, one thing it does is it lets us use like this range operator quite conveniently. But when I came to run it and did like 100,000 100,000 walks, it got a little bit slower. So I thought maybe I'll try and do something a bit more clever to make it go a bit faster. It didn't really make that much difference, but I set this array because we know how many steps that we're going, well, if we know how many steps that we're going to take, and we kind of like do, so we say here we're going to take like 100 steps. Well, in that case, let's create a NumPy array, and effectively an array in our memory, and split it into 100 steps, and then every time we take a step we can populate it. So kind of like dot 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 dot, there's 100 of these, and every time we take a step we can populate it with a number, and 1, 2, 3, 4, and so forth. We can keep populating it with numbers as we go on. So we can do this by setting this array here. I use np.zeros, and that is just a whole bunch of zeros. And this np.zeros, if I hover over it, it says shape here, and there I've just specified that it's number of steps, so it's going to be an array of size 100. Basically, it's going to start off with 100 zeros, and we're going to replace the zeros. And then also the advantage of this dtype part here is that the normal defaulting type is float 64, so we can shrink it down because we know that our numbers aren't going to be so big, so we can make it a float of type 16. So we could effectively condense our memory, and so like it's just it would be a tiny bit faster for larger numbers of runs, and there's other tips and tricks that we could do to make it faster. But anyway, what we then do is we start our loop, and I've used, instead of using res for result, I've used art. We start at 0, so our first element is going to be 0. The first value in the random step is going to be 0. And then again, we've got this same feedback loop that's going on. So I'll just do an undo of that one. So this random step gives us this R, and then this R feeds straight back into here. It'll be at the next point of our starting position. So we've got this loop thing, this cycling loop going round. And I actually had to do a round of this because I had lots of floating points, numbers that were cropping up that were like made the the floating point error when we do a multiply. So rounding just tidies it up a little bit. And I think here that I could actually just call inside, because we could do this test for it inside our test now. Instead of doing this test, we will now just do our random walk. So random walk, and again, we don't need to, like, if we don't put anything in, we're automatically going to default to 100 steps, and the random walk is going to return back something that we've called path, and path is basically the that array, effectively this NumPy array. So if I hover over it, should say this ND array, which it does do of type float 16. So it's going to give us back an array of 100 elements long. So we can have that as a result, and we could print out this result just to test the result. So we could print this out, F5 to run it. And it's done 100 steps now, and this is the NumPy array that comes back. Remember, we started at 0, and so then it went to 1, 1.87, and so forth. And it looks like it ends up, and this one ended up at 19. And I wonder if, for example, our random walk, we just put in, well, let's just try run our random walk again, just see how these actually look. And we could put this into a for loop and run it. So we could do like 10 of them, but let's just run it like this one by one, just have a look. So our first random walk ended at 19. The last element of our random walk, so the last element of this array here is -3, and I'm kind of looking at this last, so it's kind of like where we finished in our path. So, and as you can see, like, but kind of like vastly different numbers, as we would expect. That's what we kind of like want, these random walks. We don't want to, and again, now we finish at 7, and the idea is that we don't want to keep on having to run this. And so one thing that we could do is stick this into a for loop and create lots of random walks. So for I in range, and then say, like, 10 of them. Let's remove this pass statement, and then to like tab this out here. And so create like loads of these random walks and run our piece of code, and we get 10 blocks of our random walks, and it print out these 10 arrays that come over there. So that's effectively what we're going to do in the next part of it, which is, so we've done our random walk, but then we want to do a whole series of random walks. So this was kind of like, well, actually, one thing that I was going to do is actually plot the single random walk. So let's actually do that, because I can build that in here as well. So although we've got like all of our random walks, let's just see what happens. It will only, like, because when we finish our loop, we're just going to take the last one. But let's just plot our random walk single. And we saw that there was another function, so this already gives the clue. But basically, I was testing out how to plot one random walk, which is one of these set of 100 numbers, or however many we specify. And then afterwards, we want to plot many of these random walks. So this plot random walk single is going to, it takes in one argument over here, and the argument is the actual walk that we've got. In our case, it's the result. I could change this word result into walk now. So walk equals, and then that is walk, and therefore this is walk. There we go. So that's our walk. And if we just go and have a look at this actual function, so go to definition here, all it really is it takes in a list. We're now actually taking in a NumPy array, so it's actually an np.nd array, but we can take in a list. It's just as good. And it creates a set of x values. Well, this is just a bunch of x values going from 0 sequentially, each integer. So basically the number of steps on our x values until the end of the list. That's all it is, the length of the walk. And then y is actually the values that we're going to walk. And then we can just do a plt.plot. So this is from matplotlib. And we can plot the x and the y coordinate. And I've actually color coordinated it, although we won't see it for a single walk. But we can have some kind of colorization, and it doesn't, like, normally colors go, so the normal color RGB thing is 0 to 255, and then that's for the reds, and then 0 to 255 for the greens, and then 0 to 255 for the blues. So that's our normal RGB would be picking like a number between 0 and 255 for each one of these. So we'd have 3 things in our tuple, but the way that color is defined in matplotlib.plot, the way that it's defined is just a value from 0 to 1, so kind of like a percentage. In a way, it's quite nice to have a percentage. So 1 is 100% of that color, and 0 is none of that color. So this is 50% red, no greens and no blues. That's all that means. And we can plot a title, a label, and an X label and a Y label, and we can do the plot.show, which will run it. So When we run this piece of code now, our test code is going to plot all of these 10 things. We don't, in fact, let's not even plot the 10 things anymore, because we can assume that they're done, and we can see our single walk. So if we run our piece of code now, we indeed, here it is, I'll just pull it in, we see our random walk, and it kind of like it started with 0. We can still like see this jittery like pathway that it takes. And we can do something like, I guess, random walk. We can make our random walk longer. So let's make it 1,000 steps. So that's 1,000 over there, just for the clarity, and run the same thing again. And it's opened on the side. And we see with 1,000 this time, it's got like it's kind of like walked upwards basically. And basically, when we make our numbers larger and larger, we are expecting ourselves to go up. And the reason that we're expecting ourselves to go up is that we've got this drift term over here that's in there, and our drift is always 0.1. So on average, we've got 1,000, so 1,000 times by 0.1. So on average, we would have climbed about 100 just from our drift terms. So where we're actually expecting to be with pure drift at 1,000 is if I was to be able to draw this properly across, kind of like, so like that's our 1,000 mark over here. This is actually where we expected to get without any drift or diffusion, and this is actually where we kind of like got to, which is, let's just say, this green one over here. So our randomness, or the random walk in our particular case, was this little difference over here. That's effectively what we've created, and I could keep running this. So I'll just run it like a second time. Also, and also, like, if we make the number of steps something smaller, like just like 10, then we won't have enough, because again, our calculations, but let's just pull this in on our calculator, we'd have 10 times by 0.1. So we'd expect to finish around the 1 level, but with some randomness that's in it. But the randomness is now quite large relative to the drift component. So let's just do that anyway, just to do it. And indeed, like, our random walk looks much more random in that case, in that sense, because our drift term is less significant relative to the diffusions, because we just simply got less drifts. Now we've only got 10 drifts in there. But anyway, that's basically it. So we can create one random walk, and now the question is which we can plot our single walk. We plotted our single walk using Matplotlib quite conveniently. So the next step was, we kind of like done all of these bottom bins. I'm kind of like working my way up, building more things in here. The next bit was plot walk many, okay, which is basically plot many random walks. And in order to plot many random walks, it's actually not that dissimilar. And really, it's a case of, and I had to kind of like think about this basically. But in our test example, can we put this walk, like what structure, data structure, do we want to put it into? And I was like thinking that there's two obvious ones that we might want to go to, which is basically we could have a list of lists, or we could have a, because these are collections basically, we could have a dictionary of lists, right? The list of lists wouldn't have the keys for the key value pairs, but you could say that you don't need them. I just went for the dictionary because they basically, you've got some labeling that helps you, but either could have been done. In fact, the list of lists in a way would have been kind of like faster and easier to do, but a dictionary of lists is fine too. One advantage of the dictionary of lists, not that I use this advantage, is that we could use a pandas. We could stick this straight into a pandas data frame. We could also stick the list of lists into a pandas data frame as well, but this one just fits in, I think, without literally doing anything. We could have literally used the pandas module and passed it straight in, like with its most simplest kind of like format for doing it. But I never needed to go there, but I was thinking I'll do that just in case I wanted to go there. So no, I want to create this dictionary of lists, and I need to initialize some sort of dictionary to start with at the beginning, which will look something like this. And then we need to keep on appending our dictionary. So something like dictionary of I will be equal to walk. So we create a random walk, and let's just make this, we'll let it default to its 100 steps, and then we pass it into the dictionary like that, and we should have a whole bunch of dictionaries. And in fact, if I was to print out D, just do print D in fact, so we won't print our single walk anymore, we'll comment that one out. But now let's just do print, so we'll plot the single walk, we'll plot the dictionary here. And I think that might just be sufficient on its own to create a dictionary that contains a whole value of random walks. So if we run this, hit F5 to run it, I'm hoping that this one works because I'm doing it kind of like live. Yeah, we get a bunch of dictionaries, and this is dictionary number 7. The nice thing about this is that our dictionaries are labeled for us. So this is dictionary 0, and it contains 100 items in it. And then this is dictionary 1, which is an array which contains another 100 items in it, and dictionary number 2, which is another NumPy array which contains another 100 items. And we've got 10 dictionaries here. So now, having done that, we've got a whole bunch of dictionaries. It wouldn't make sense to keep plotting single walks, because if we kept on calling this plot single walk function, we'd have this chart pop up, and then another chart pop up, and then another chart pop up, and that would be rather annoying. We'd have to do that 10 times and close the charts, which we could do. Maybe I'll do it for a small version of it, like I'll do it for like 5 steps, because it may be not too annoying there. We could now plot our single walk like this, and we could plot the dictionaries, so DI, so each one. In fact, we would need to put our plots inside, so we'd create that. And in fact, we could actually just plot the walks. We didn't even need to plot the dictionaries, but whatever. We can do either or now because we've now created it anyway. So if I do run this code again, I'm hoping that this one will work. We should get 5 plots that pops up. So that's our first plot, and then this one ended up at, if you just look at our end value for sanity's sake, it ended up at 5. If I close it, the next plot opens up. I have to keep dragging them on because my plots are opening to the side. This one ends at 2. I'll close this one. We're on plot number 3 now, that ended at 17. This is our 4th one that ended at somewhere between 6 and 7. And this is our 5th one. It ended at 17.5 or 18, something like that. And that was the end of it, and then our code ended. But that was rather annoying because I had to close it 5 times. So what we're going to do instead is the next function. We want to create a function where instead of plotting this inside of the for loop, we want to kind of like take this outside of the for loop, and we want to plot many. So something like this. And how will this many actually work? And I spent, to be fair, like a lot of the time is kind of like customizing Matplotlib, how you want your Matplotlib to look, basically. So we're going to comment out this single, which was actually inside of here because we don't want 5 of these. But now we want to plot many, and we want to what we do know that we want to pass in is this dictionary. So this is a dictionary, right? Dict, right? And in our like type hinting of it, let's have a look. Plot many. Oh, sorry, I don't need to specify there. We're passing this dictionary, and if I hover over it, I've already got the hinting, but we'll go and actually look at the function. But we want to pass in a whole bunch of dictionaries, and the keys for the dictionaries are the integer numbers, like that we've counted, so 1, 2, 3, 4 each time we create one of these, and then we've got a list, which is the actual path that we're going to pass in. In our case, it's not just a list, it's a NumPy, it's an ND array, so it's an array of numbers. And then it returns nothing back because actually what we're going to do is plot all of the walks that are contained in the dictionary. So let's just jump to this plot walk. So go to definition, and here's a doc string, plot many random walks, and I wonder if I could actually put in, which is an nd mp.nd. Right, that's actually what's going in there. It's no longer a list. It's an NumPy.nd array. Is what we say that we want to get in there for plotting. the more that we can avoid lists and use arrays and stuff, the faster our code will go. We lose a bit of convenience for doing it, and maybe it's less readable. That's kind of like, there's always pros and cons with this stuff. But anyway, I felt it needed, like our doc string needed something to, like a little bit more explanation for somebody else who's looking at it. But the argument is this dictionary, where the key is this integer representing the, well, let's have the walk value. So where keys are integers representing the walk number and values are lists, which is now np.nd arrays. Right, they're NumPy arrays of floats for the walks. Okay, so that's effectively what they are. I might shrink this down just and call it list, just for the sake of it. But we've kind of got a little comment in here. We can use something a bit better than a list. But anyway, what do we actually do then? We need to iterate through our walks, and we just do for kv in walk.items. That's a typical pattern for looping through looping through a dictionary. Walk.items will return us back the key value pairs that come out. We assign the keys to k and the values to v. So this thing returns tuples each time, a key and a value. For the first step, the first index is 0, so k equals 0, and then it will be the first walk, a whole bunch of values for that, and so forth. Now, when we've done that, the next thing we want to do is set our X components. Now, this again is repeated. We could really take it outside of the loop, because if we know how long our walks are, then we don't need to keep reconstructing our X. Now, I'm just going to assume that for whatever reason, we might have wanted to vary our walk length sizes if we did want to, but so it's inside the loop, but again, an efficiency gain if we were to kind of like move it over here outside of the loop in some way that would gain us efficiency. So we create our X values, we create our Y values, and we do exactly the same plot X and Y. And this is kind of like what the nice bit about the color bit, which is it's split into 3 components. So this is the red. The first section here is the red component. In fact, I'll circle it. This is this is the value of our reds, and I've made it a little formula going in here. This is the value of our greens, so there's no greens, and this is the value of our blues over here, so there's no blues either. So it's basically shadings of red, and I basically said just use k, whatever k is. So k is going to be like an index of some kind, and then divide it by the number of walks. So because I'm just trying to think if we ever go over the number one. Well, I don't. Length of walk, so long as the length of walks is long enough, we'll never go over that value. But even if we did, we'd normalize it back down to make sure that it's less than 1. But basically, it will go from k starts at 0 because it's our first index. It starts at black and then becomes like lighter and lighter red. Basically, that's what it does until it gets to 255 reds, and then after that will be 255 over length of walk. So just keep getting lighter and lighter. That's actually what would happen. So that's our colorization, and then we've just got the same title, label, and the title, the X label, the Y label, which was fine. And then I kind of wanted to plot the statistics of the walks. I'll go into that in a second, and also to like plot them nicely on the chart. And also, I did want to plot a legend, but if to identify which walk was which. But if we have more than like 10 walks, and we're intending to do like 1,000 walks or something like that. If you have more than 10, then the legend just starts to get illegible, so you can't really read it. So I've done an if walks is like less than 10, then we'll print the legend out. Otherwise, we're going to omit the legend. So it's basically going to run now, and I'll go through the stats a bit later and plot walk many, I think it should run as is just from this test code. So if I do F5 to run it, we might get a legend actually. Yeah, we do get a legend. We get a legend over here because we've got 0, 1, 2, 3, and 4 because we ran it 5 times over here in our for loop. That's actually quite nice. That was an accidental, really nice thing to pop up because we do get our legend, but also like you can see that there's some stats that go out here, and we can see now that we've got our random walks, and our first walk is black, our next walk is a bit less black, and so forth, and it gets more red and more red. So our last walk's this one, so we can like see the walk paths on it. Now I guess if I do 9 it will be acceptable because that's still less than 10, so we can do 9 walks on here, and then we'd lose our legend afterwards. So 9 walks gets plotted. There's our 9 walks. Some game starts at black and gets lighter and lighter. So we can kind of like see our first walk was here. Potentially one of these ones looks like this one looks the most black. So I'm going to just say that that's our first walk, and our last walk was here. But this is kind of like where they all ended up. And we will look at the stats. Basically, what I'm interested in is kind of like what is the average of the ending points, and it looked like the average here was 9.52, and kind of what's the standard deviation and what's our maximum value if that happened to be the last walk, so that maximum value, and what was our minimum value. So kind of like some stats just to measure it up. And kind of I guess if I hover over here, if you look at this bottom corner bits over here, you can see the numbers, and so like I don't know where the average is, but 9.52, so it's sort of like over there was the average. But anyway, we're going to get a bit longer. So now we'll do the 100 walks over here, for example, 100 steps. And it doesn't make sense to have a legend that's 100 long. So we won't get a legend. But our random walks begins to look like this, like a whole bunch of spaghetti, which is great because that's kind of like what we want to achieve or get to, and we want to get our stats. So let's just go in and look at the statistics of this. So we'll just go to our plot many, go to definition. And one nice thing about writing everything in functions is that you can break it down into little pieces. And I kind of like I want to get the statistics and plot it on the chart. So this is how I would plot it, or this is how I would calculate it. I create this function, and this function exists somewhere, so I can go to definition of the function. So what is the stats of our walks? And basically we set up this, so given a dictionary of works, work out some interesting statistics. And I was just like, well, let's get the mean, the standard deviation, the max and the min, but there's a whole bunch of other things that we could potentially do. But anyway, we'll start with that. So for walking walks dot values, so let's just take a look at the values, right, which is our dictionary of lists. So remember that we've basically got a whole bunch of lists like this. And they're all labelled with our dictionary, so it'd be 0, 1, 2, and so forth, down to 100 or however many we did. 100 over here. So that's what we're doing, and we're saying just take the last item of it. So we've created this empty array. So let's create this empty piece of memory for storing our values, and from each one of these, take the last item, take this item, and place it into the array over here, and take this item, the last item, and place it into the array over here, and so forth, and keep on doing that all the way down until we've filled up this array. So we've got all of our last items, and that means that we know all of the finishing points, basically. That's why I called it endpoints, because we know all of our endpoints, and now it's in an array. Now, if we've got everything in an array or in a Python list, then we can operate on the list quite nicely. And we can do that with the, there's a couple of different ways. I could have actually just done it with the NumPy module. So these are some modules, but I chose to do it with the stats module. I could have done it with a NumPy module as well, because it would count. It does basic statistics as well. But I just thought, you know what, just for the sake of niceness, let's use the statistics module because it's quite suitable that. And let's calculate the mean. So we passed in all of our endpoints, that whole list that went in, and we can calculate a mean, a standard deviation, a minimum, a maximum, and actually also, and then afterwards I said, well, let's put in the length as well. And I'll put that all into a nice dictionary. Why a dictionary? Because that dictionary is just easy. We can return an entire dictionary. Now, if we return an entire dictionary, then we can, I just wonder if I go to definition here, let's see where it takes us to. Okay, I should go to references. I won't even bother doing that. Control F in our code and then just find it. If we can, so this is where it actually gets run. The stats of the walks. We take in all of our walks and it returns back. We see here that it returns back this dictionary, and we can put this dictionary straight into this variable which I've called stat. And then I've had to make some kind of string because I don't think that I could print a dictionary, so I've converted this dictionary into a string that looked quite nice. Not amazing, but it looked nice enough that we could see our statistics, and then I plotted it on the chart. So that's what this little section of code was for the purpose of plotting on a chart. I could have broken that down into another function, but it kind of like, since it was part of the plot, I left it in the plot section. So it plots the walks, and that's pretty much it. That's all of the random walks. Now, the one final bit was, I was kind of like, well, let's just see once we've done all of this how long it takes. So we no longer need this test method to run because we've done our tests and we saw that they worked. We could go to the main module, and if we go to the main module, so go to definition, that's right at the top, and that kind of like the main entry point for the code, and it calls everything. And I was like, I just want to see how long it takes, because if I put in like 100,000 loops or 10 or 10 walks, like how many walks we actually want to do. So like how long is it going to take for our code, like the performance basically. So this is going to be 1,000 walks for I in range 1,000, walk equals random walk, and each of our walks is 100 steps. We can muck around with it and see like the differences now. And we got a time 0 and a time 1, so it measures it before and after. We're not measuring how long it takes, although we could do how long it takes to actually plot the walks. We're not actually doing that. Partly because I think that this only exits the actual plot when we press the cross button on it, so it's then got some human time involved in it. So I kind of want to know what the computation time, but it does actually take time for matplotlib to collate all of these values. Now if we've got 1,000 walks and each walk is of step 100, the number of computations that we've done very simply is 100 times by 1, 1,000. So we've got 100,000 calculations going in here. And if I increase that a tiny bit more, we'll see that we'll have like 1 million calculations. If I increase that by another factor of 10, so like I made our range a little bit longer, or I made our walks, instead of being walks of 100 units, make walks of 1,000 units, it just gets a little bit longer. But let's have a little play around and see what this looks like. So now we're running the full code here. We're just running the main module, and we'll see our base one, which is 1,000 walks. F5 to run it. It's taking, let's see how long it takes. We get a little print. It said 0.714 of a second, so just below a second. And the walks came up. I have to keep dragging it onto the screen because it plots it to the left-hand side of my screen. But we can see that that's 1,000 walks. That's what 1,000 random walks looks like. And notice here that the average is 10 and 10.10, 10.1, right? And the reason, like we already said, that what we expect, which is if we've got 100 steps, and each step has a drift, not the diffusion part, but the drift component, times by 0.1, that we get 10. So we're expecting 10, and we look how, like, when we do lots of walks, we get closer. We're hoping to get closer and closer to this average. Now we're going to get a standard deviation away from it. So 65% of the data, most of the data basically, lies within. So if our average was 10, and the 10 looks like it's about here. So if our average was 10, 65% of the data should lie between plus or minus 1 standard deviation, which is something like this. And then like 90% of the data will be here. And it actually does come out to be, even though I haven't tried to do anything other than using the random module. So other than using this random module at the top here to generate random numbers between -100 and +100, I didn't do anything extra. I kept it really, really simple. It's done this, and we've got some kind of, if I was to like draw it, and if we were to draw the density of it, some kind of like log normal distribution on its side over here. It looks like that. That's effectively what we've got. So I'll just remove that. So that was for 1,000 walks, and again we can see our minimum, which is -12. That was our lowest walk of 1,000 walks. That was our minimum ending point. So even though we had a drift, and our drift should have looked like, if I draw it over here, our drift should have looked like something like this on average, going from 0 to 10. We did get 1 or 2 or some walks that ended up as low, and that is the walk here. So like that ended up down at this point here. And also likewise, we get some that are vastly above the 10 level. So, you know, these ones over here. So we did get those, and that was 1,000 walks. And we can just try, we'll just run it again just to see, you know, another set of numbers, whatever pops up from it. This one ran again in 0.7 of a second, so we're getting a handle on how long it takes to do these 100,000 operations, and we have not before we actually plot them, and then it gets plotted. And again we get 10.1, so like eerily close, like it's and like if I keep on doing it, we'd get the same number that comes out. But this time our minimum walk was only got our minimum value got to 7 over here, and our maximum got to 27 over here. Now we can do things like let's extend it. So let's put some pressure on our system. So this is 10,000 walks, and that would be 1,000,000 computations because it's 10,000 roughly, crudely speaking. It's 10.3 times by 100 steps. We're doing 1,000,000 computations, so you know, let's see how long this takes. And this is kind of like where you say you start needing to think about improving the Python code that's run, you know, do other things. Because when I run this, I will do it now and then talk about it, but it's going to take, if this took 0.6 or 0.7 of a second, then this one we're now 10 times longer, so it should take 7 seconds, and it does. It says 7.4 seconds. And I'm waiting for the chart to pop up. I'm not, it hasn't yet popped up. This is also taking time to draw the chart, and hopefully the chart does get drawn in a second or two, and then I'll be able to drag it on the screen. So our chart has been, it's being rendered now. Which actually took some time. It took a good 5 or 6 seconds for the matplotlib chart to come up, and that's now 100,000 walks with 100 steps. And if I did a longer one, it would be like made the steps longer. So now I'm kind of like, at least for how we're using Python with its 1,000,000 steps, doing it this way, I either need to think of getting more efficiencies in terms of like the data structures that are used, or alternatively, can I do some mathematical tricks, kind of like just like do every 2 steps and other things like that, in order to like save some computations. Because what we do see is every single one of these charts looked similar. They all have similar form. Very, very dark in the middle. This got to 10.02, by the way. Very dark in the middle, because it still is like normal distribution. And then we've got like our end points over here. You know, and effectively, it looked, we had effectively like this same sort of like normal distribution pattern, or we can't see it, but it's highly dense in the middle here. Like all of our walks are here, and then like our extremities are down the end. So there's things that we could do to do it. Now, if I was to run it longer, it'd be 70 seconds. That would be 1 minute. But let's actually think of an alternative or something that we can do, so that I don't have to run a 70-second piece of code and wait for it, which is, well, one thing that we can do immediately is we just do the same 1,000 loops, but this time let's make our walks a bit longer, because we haven't done that yet. So this was our first argument that goes in here, which is number of steps. And I'm just going to label it n steps equals, just so that it's clear for us. And we're now going to do 1,000 steps in there. There we go. I like to use the underscore because it's clear. So we've now got 1,000 walks containing 1,000 steps, and 1,000 times 1,000 is 1,000,000. So we've got the same million computations. That should only take several seconds, hopefully, and then another 5 or 6 seconds to render it onto the matplotlib plot. I'm wondering if it actually does it a tiny bit faster. So it's done the 7 seconds. I think it's done it a bit faster because it's plotting less actual lines. So that's one trick in itself. Now we go from 0 to 1,000, but just remind ourselves that the 0.1 step times by 1,000 steps, we're expecting to get to the 100 mark. So we're expecting to sort of like, I don't know if I can do a dotted line here. We're expecting, because this is by hand, I'm not drawing it on anything. So we're expecting to get to there basically. That's sort of like our midpoint. And then our volatility points again are out here. That's our edge case, and down here is our edge cases again. So that's pretty much random walks in Python. I've covered a reasonable amount. I've done this in a functional way, functional programming. I've used a couple of different modules here, but I didn't have to. I could have probably got away just using the NumPy module. So I've thrown in the stats module and I've thrown in the random module. For example, I could have done np.random .rand int that generates these random integers. Excuse, I've got a phone call which I'm going to hang up on. That was a standard junk phone call that comes in once a day. So there I could have done random ints. Now the reason why I didn't like that is because I saw this curly bracket here, which means exclusive. So you've got inclusive and exclusive, whereas the rand int, apart from being less in terms of thing here, both of these, I see a square bracket and a square bracket, which means it includes both its endpoints. So it's just less for me to think about. So there's things like that which you can choose. There's a whole variety of things, and actually one thing that you could do. So this is an exercise for anyone watching, and even myself. Maybe I'll try and do it on a follow-up video if I get time. Is change the distribution pattern that goes in there to kind of like skew that, instead of just using a random number between 0 and 100. Well, how about using a random distribution between like -50 and +200, so it's skewed that way, or even picking a distribution for the skew to go in, so some sort of exponential distribution or something like that, log normal distribution. So there's a whole bunch of things that that can be done, and if you were to do that, then maybe you wouldn't need the drift component in there, because effectively that's creating some form of drift. Because if we did have a probability distribution that looked like this, so kind of like skewed to one side, that we could hypothesize that our drift is now this difference here. So it's kind of like manufactured into our probability distribution, whereas our normal distribution, what we might have expected in a symmetrical distribution is this. So we could create an asymmetry in the distribution to create a hypothetical drift. So I just like created one model. I've used the drift and diffusion terms because and I've kept them separately as separate components, and the reason that I've done it is because that used to be a common thing in finance. Well, it still is, because if you want to model the risk-free rate, you could bake your risk-free rate into your distribution, but you could expose it like directly. So that's kind of the maths of it. And I think that's it. If you like this video, if you found it useful, certainly follow, leave a like, and so forth. If there's any questions, definitely put the questions in the comments. If there is, I'm going to actually delete this little component of it. I'll leave it like that as it's standard. if there's any, aside from questions, if you've got anything that you feel that could be done better or improved in some way, or you've done your own random walk, there's plenty of different random walks because you can take them off the web. But if you've done your own one, you know, by all means, kind of like send links to GitHub and so forth, and put your comments in there. And that's it. So that is 1,000. I'm going to call it 1,000 random walks. 1,000 random walks in Python, using Python. That's it. Thanks for watching.